Welcome to lesson 9. Here we're going to be looking at the motion of objects, thinking about position, velocity, and acceleration, and linking them to the derivatives of a position function. All right, so to start off, go ahead and complete the following 5 questions. You really don't need to write down all of the questions. You simply need to write down your answers to help formulate and solidify your understanding of the relationship between a particle's motion and the various derivatives of the function that describes its position. All right, so when we are thinking about the position of a particle or any object, the position is measured as a distance, a distance away from an origin, or in this case we're thinking about the x-axis. So the position along the x-axis would be the distance that is away from the origin at a given time. Now when you think about the derivative is telling you the rate of change. And so the rate of change of position is a certain amount of distance over time. And that is, in fact, velocity. So the derivative, x prime of t, is the velocity of the particle at any time. In other words, the instantaneous rate of change. When I think about the second derivative, remember the second derivative is the instantaneous rate of change of the first derivative. So if the first derivative models the velocity of the particle, then the rate of change of the velocity, in other words, how the velocity is changing, is the acceleration, right? Think about if you're driving in your car and you're accelerating. That means you're changing the speedometer's value from maybe 20 to 30. In other words, you're changing your velocity. You are accelerating. So important to note, I have a function that models position, its derivative models velocity, and its second derivative models the particle's acceleration. So if a particle is moving to the right, what does that mean about the derivative? Well, the first derivative, remember, is the velocity. And so if you're moving to the right, we consider that the positive direction on the x-axis. That would mean that your velocity would be positive. Accordingly, conversely, if you're moving to the left, you would have a negative velocity in this situation. If a particle is at rest, what must be true of x prime of t? In other words, the derivative, which is the velocity. Well, if your particle is at rest, that must mean that your velocity is 0, right? Because you're currently not moving at all. So your position is staying the same. In other words, your velocity is going to be at 0. You'd have a horizontal tangent at your position function. How could you find the time when the velocity reaches its maximum value? Well, here you're trying to find the maximum velocity. Well, if you have a function that models velocity, how would you find a maximum value? We've done a lot of work with maximum values, right? Finding the relative maximums, minimums, absolute minimums. So if you're given a function, v of t, or you find that function by taking the derivative of the position function, how would you find a maximum value for this function? Well, the same way that we've talked about finding the maximum values of any function, we can use that model to find the maximum values of this function. So thinking about the first derivative test, what we want to do is we'd want to take v prime of t. Now notice, this is the acceleration, a of t. And we want to set that equal to 0, or find out where is it undefined. Right? Those are the critical points. Okay, so we have those critical points, and then we want to make a sign chart, right, for our derivative, or in this case, for the acceleration. And we want to know, if we have a couple of critical points here and here, and this is a sign chart for our derivative, v prime of t, which is also the acceleration. We want to know where the acceleration is changing from positive to negative. Now, notice that if you're accelerating, that means your velocity is increasing, right? The derivative velocity. So your velocity would be increasing, and then it would start decreasing. So this would be a relative maximum for the velocity. Similarly, this critical point would be a relative minimum because the velocity would be decreasing because the acceleration is negative. So your velocity is decreasing, and then it starts to increase. This would be a relative minimum. And so then we can use these derivative tests to find the maximum values of velocity, the maximum values of position, and so on and so forth. All right, so let's really formalize these relationships and look at graphical representation to help solidify our understanding. Okay, so here's the basic relationship. When describing motion, I have a function s of t that describes the position of an object at a time t. Then the derivative of the position is equal to the velocity at that time t, the velocity of the object at time t. Now, one thing I encourage you to write down here is that the derivative s prime of t is the instantaneous rate of change of the position, which is velocity. How is your position changing, right? That's what velocity is. S double prime of t is the second derivative, so it's the derivative of velocity, meaning it's the instantaneous, I encourage you to write this down, the instantaneous rate of change of the velocity. In other words, at any instant, what is your velocity changing? At what rate? In other words, that's the acceleration, right? That's the term we use for it. So this would represent the acceleration of the particle at a time t. There's one other key distinction to make, and that is that you often hear the phrase speed. So speed is a little different from velocity. Velocity tells you the direction as well as the speed, right? So if you have a positive or a negative velocity value, that tells you whether you're moving to the right or to the left. Speed is the absolute value of velocity, because speed doesn't care whether you're moving in what direction you're moving. It just cares the rate at which you're moving. So it's the absolute value of velocity. All right, so I want to take a look at just a couple of graphical representations to help make this very, very clear. All right, so take a look at this graph here, and I just want you to really try and internalize this. So let's say here is my function s of t. This gives me the position of a particle at some time t. And right at time 2, I've drawn the tangent. Remember, the tangent has the slope of the derivative at this instant, 2. So this can really give us a visual representation of what the velocity is right at this instant, right? What's the rate at which the position is changing? And we notice that this has a positive slope, right? And so we can see, like the velocity should be positive right at this moment. Now, if we took the derivative of this function, s prime of t, which is 3x squared, if we took the derivative of this function, we'd have 6x, right? Okay, now if you graph the function 6x, what you're going to get is a straight line. Let's go ahead and take a look at the graph of that function. All right, so here is the graph of the velocity, v of t, which is the derivative, s prime of t. And we can see here this is the function 6x, and if I go to time 2, and I go up here, okay, well that's a value of what appears to be around 10, maybe 11 or 12. And so that is the slope of this line right at time equals 2. And we can see that that should make sense. This line certainly has a positive slope, and the value of the velocity at time 2 is a positive value. Now let's think about the acceleration. How is the velocity itself changing? Well, notice the velocity is increasing always, and since it's a straight line, it's a linear function, it's always going to be increasing by at the same rate. And since this is the function y equals 6x, we know that the slope of this line is 6. So what we expect when we take the derivative, we're going to have that the acceleration, or s double prime of t, or the derivative of the velocity, is just going to be a horizontal line at 6, which tells you that you're constantly accelerating. Let's take a look at that. All right, so here is the second derivative, s double prime of t, which is the derivative of velocity, which is acceleration. And let's just take a look at the relationship between all of these. Notice that if I'm starting with position, the position is always increasing as we move to the right, right? And that makes sense when we look at our derivative. In other words, we look at the velocity. The velocity is always going to be a positive value, which means that our position is always increasing as we move to the right. But also, we're not just moving to the, we're not just increasing. We're increasing by more and more. In other words, our velocity is increasing, as we can see here. And that is evidenced by the acceleration, which is always a positive value, which means that your velocity is always increasing. And we can see the relationship here. The acceleration is positive. We have a function which is concave up. Okay, that should make sense. Also, our acceleration is a positive value, which means our velocity is going to be increasing, since acceleration is the derivative of velocity. Hopefully that was helpful. Maybe if you're still a little confused, looking at an example will really help clarify your understanding. All right, so go ahead and work on this question first on your own. You have all the tools that you need to answer all these questions. Just make sure for each one that you, before diving in, know what it is that you're looking for and how you're going to find it. That'll be worthwhile so that you don't waste any of your time. All right, so when I tackle this situation, the first thing I want to recognize is that I am given the position. So if I'm given the function that models position, I can find a function that models its velocity and a function that models its acceleration. And so my hope is to use these in conjunction with each other or independently to answer the questions that I'm being asked. So let's go ahead and dive in. We have a question that asks for the initial velocity of the particle. So initial means at the very beginning, in other words, when time is equal to 0, and velocity is the velocity of the particle. So here, that means I'm looking for v of 0. Now, what am I going to do to find v of 0? Well, I know that velocity is equal to the derivative of position. So I'm going to find the derivative, and then I'm going to evaluate when t is equal to 0. All right, so here we go. I want to find the velocity function, which is the derivative of the position function, and that is going to be 6t squared minus 28t plus 22. And of course, this is when t is greater than or equal to 0. Once I have this function, I can now find the initial velocity by evaluating when t is equal to 0. But we can see that this is going to be 22. Now, it's a velocity, so I want to write this in terms of, the units that it's actually measuring. So I don't have a specific unit of measure for the position, but I do know that time is in seconds. So I can just say that this is units per second. All right, next I'm going to be looking for when the particle is at rest. And here I'm thinking, okay, when is something at rest? Well, that's when it's motionless. So here I'm looking for where the velocity is going to be equal to 0. So I'm trying to solve v of t equals 0. What is the acceleration of the particle at this time? Well, that means I'm going to need to use the acceleration, and I need to plug in this value that I've found that makes the velocity 0. So once I've found this value of t, I need to evaluate the acceleration function at this particular value. And that will tell me the acceleration at that time. So I have the velocity, and I need to set that equal to 0. So I have 6t squared minus 28t plus 22, and I set that equal to 0. Now, there's a couple of good strategies here. The one that I would recommend is trying to factor. If not, you can utilize the quadratic formula to solve this quadratic. So why don't you go ahead and try that on your own just for a little bit of practice. We'll take a look at the solutions in a second. All right, so if I factor here, and what I can do is I can factor out a 2, and then I'll have 3t squared minus 14 plus 11, and then I can factor that a little more easily. And by doing this, I can solve for the values of t that will make the velocity 0. So when t is equal to 1 and when t is equal to 11 thirds. So these are, of course, seconds after 1 second and after 11 thirds seconds. And now I need to find the acceleration function in order to plug in these values. So acceleration is going to be the derivative of velocity. Well, the derivative of my velocity function is going to be 12t minus 28. So now I can plug in these values, right? The acceleration at time 1 and the acceleration at time 11 thirds. So why don't you go ahead and find those accelerations and do your best to put the correct units there. All right, so finding the acceleration at each of these times, I get that at time 1, the function, the particle is accelerating at -16. Now, the way that I write this is not in units per second, but units per second squared. And I write it like that. All right, units per second squared. That's how I write acceleration. All right, so I found, what's interesting here about this result is that when the function is at rest, it actually has an acceleration. The velocity has an instantaneous rate of change at that point, even though the velocity is actually at 0. And I think that's an interesting point that it comes out of this question. Last but not least, where is the particle changing direction? So here what I want to know is where is the velocity changing from either positive to negative or negative to positive. So the best way to look at that is to make a sign chart here. And I've already found the critical values of my velocity, the two values that make my function 0. And so if we can actually just use this little space here. So if I look at my velocity, my critical points are at 1, that makes the velocity 0, and 11/3, that makes the velocity 0 as well. And now plugging in values here, I will see that my velocity is going to be positive, negative, and then positive. So the function, the particle itself, the original function, is actually going to be changing the direction in which it's traveling. So this particle will have a velocity that's positive from 0 to 1. Then it will have a velocity that's negative from 1 to 11/3, and then we'll have a positive velocity from then on out. So right at 1 second, the particle was moving to the right, and then will change to be moving to the left. But then at 11/3 seconds, the particle will stop moving to the left and begin moving to the right. So at each of these times, the particle will be changing direction. All right, I'm going to give you a couple more now to try, so go ahead, head to Math Excel and work on 4.09 homework, and this will give you more opportunities to utilize both the first and second derivatives of the position function to make sense of particle motion.